So the nice thing is the antiderivatives aren't terrible. Let's see, sine plus cosine, and we're going to go from 0 to pi over 4, plus the next one would be negative cosine minus sine, pi over 4 and pi over 2, right? So if we do our evaluation, sine at pi over 4, square root of 2 over 2, cosine square root of 2 over 2, so that would make 2 square roots of 2 over 2. All right, minus the sine at 0 would be 0, the cosine would be so minus 1. And then the next one, if we plug that in, opposite of the cosine at pi over 2, that's going to be 0, minus the sine at pi over 2, so that would be negative 1, minus, and then we plug in pi over 4, so negative square root of 2 over 2 minus square root of 2 over 2, so plus 2 square roots of 2 over 2. So the 2's are going to cancel, correct? And it's going to give me a square root of 2, 2 square roots of 2 minus 2. For an exact answer. Did I do my arithmetic right? I did a lot in my head because I ran out of space. Okay. So main thing on that one is recognizing that you've got two regions there. They intersect at pi over 4, and they swap who's on top. All right, when that happens. With the second one, we're looking for the value of k that would make this equation true. So they give me, and this one's calculator active, they give me an integral, and we know what it's equal to. So if we take an antiderivative, that would be x cubed plus x squared, evaluated from k to negative 1, and it should equal 80. Right, so if we plug that in, k cubed plus k squared minus negative 1 plus 1 equals 80. So the ones would cancel out. K cubed plus k squared equals 80. And we could put that on our calculator and solve for k. All right. Is it 4? Okay. Yeah, I didn't have the answer in front of me. There you go. Okay. So question on those two. All right. We'll have a warm-up every day, usually ones where we'll just show the work just to practice some things, okay? I did find you another quote for today. All right. I've got one for tomorrow, too. I already picked it up. Before anything else, preparation is the key to success. But felt appropriate for what we're getting ready to do. Okay. Alexander Graham Bell. Our review target today, we're going to talk all about limits and continuities. Just been a hot minute. Okay, all that stuff still comes out and into play. The next few pieces of information are just some general things about the exam itself, okay? Main thing, it's a 3-hour and 15-minute test, okay? So it's a long time. You guys know your calculus, but you get tired. You will get tired in there, all right? So that's why it's good to sit for a whole one. The first multiple choice question, or the first multiple choice section, part A, 30 questions, you have 60 minutes. Second part, so that's your no calculator, and then you have calculator 15 questions for 45 minutes, calculator required. Then you get your free response. There are 6 questions, okay? You get 30 minutes to do the first 2, 60 minutes to do the last 4, basically 15 minutes a question, all right? Some questions will not take you the full 15, others might take you 20, okay? So just as a heads up. Loose scoring chart, okay? Note that this changes year to year, but this is pretty close to what it stays, okay? If you notice, it told you that half of the exam, and I'll tell you this, it's 54 and 54, okay? For a total score of 108. So you can see where doing well on the multiple choice puts you in a good position, okay? Free response is the bonus, it's what will separate you from the top tier, okay? So that's why it's important. It's also why I focus so much on the multiple choice throughout the school year so that we're ready when we get here and we can spend more time looking at the free response getting there, okay? I've not known anyone to get a perfect score on the multiple choice, but you can earn a 3 with just the multiple choice. All right, so, but you got to do really, really, really well. All right, and there are always questions within there where only like 2% of the people who took it got it right. Okay, so they will put some really tough questions in your multiple choice for that reason. Okay, they want you to have to prove your mathematics in the free response. Okay, all right. Stuff you must know cold. Now, for those of you that picked it up, that's the blue sheets. If you look online on your Google Classroom, it'll show you all of that. I did not pull it into my presentation just because it's so many pages, but it is full of everything that you need to know on the AP exam. It's a lot. Okay, these are all your theorems and definitions. There's just a lot there. I did mark off some stuff under the trig identities. Okay, you do not have to know double angle or power reducing formulas. Okay, so if that's, I don't know if I'll mark that off on your blue sheet or not, but you don't have to know double angles or power reducing formulas. And then under the basic integrals, you don't have to know the integral for tangent, cotangent, secant, cosecant. All right, those are special, and we don't have to do that, nor do we do the shell method for volumes of solids of revolution. Okay, so those are no longer tested on the AP exam. Gives you some integrals, some derivatives, some basic functions. So this is just a really good reference sheet as you're preparing, okay? If you're like, gosh, I don't remember, go back and look. That's what this is for, okay, to help you with that. On AP Classroom, I don't assign these videos, but they are really good, okay? So if you look, they have 4 years, all right, and there's 2 weeks of videos, so there's 10 videos for each one. 2024 and 2023 are style specific. So if you click on those, and if you go under AP Classroom, you'll click review. This is what it should look like on your side. Actually, I think I was in Jacob's account when I did this. But anyway, it should say, because you're top of the list, that's why. It lets me switch, but I have to pick a student to look at a student view. So you'll click review there underneath everything there on the left-hand side. And this is what comes up. And then you have the drop-down tabs. So 2024, 2023 are style specific. So there's multiple choice, there's free response, and they go through questions every day. 2022 and 21 are topic specific. All right. So it may say things like continuity, limits, volumes of solids of revolution, MVT, EVT, IVT. So like there are different things in there that you can go in and look at. And I believe there's a QR code attached to those you can scan to get printed copies of the documents that they walk through, okay? Some of the things that we will do will come from the 21 and 22 because I have the Dropbox that has access to that Dropbox that has all their stuff that they use, but they're good. So if you're like, man, I'm really struggling with this one topic, 22 and 21 are a good place to go to look, all right, for extra, just instruction or hear somebody else say it. Mark and Verge do these. I feel like we're BFFs, okay? We met during COVID. When they taught the last part of calculus, I had already finished, but they taught that. And we had a video every day at 6 p.m. And so anyway, I feel like we're friends. I think Verge and I could really be good friends, but Mark's kind of a butthole. And if you watch them, you'll see what I mean. So, okay, anyway, Verge had purple hair during COVID, so she was kind of my hero, all right, teaching calculus. Anyway, all right, this is content from Unit 1, all right? This is what all we covered in Unit 1. Right, it was a lot, okay? It was a lot. We did a lot of things in Unit 1, and so what I'd like to do is just to spend some time walking back through some of that stuff, all right? It's hard to believe we did all that, right? Okay, so we're going to look at several examples of different things. On our first day that we have a double class, which I can't, not tomorrow, but in the following weeks, we will take the full multiple choice of a practice exam because we have time, okay? So we'll have time to do that. All right. Okay, cool beans. Well, let's get into it. Let's rock and roll. Let's walk back through some limit stuff. All right. They ask us to look at limits in a lot of different ways. Here's the first way we want to look at it is in terms of a graph. All right, 1 through 3. Take a second, see if you can do them. Okay, see if you can do 1, 2, and 3 just looking at them. It's been a hot minute. All right, what do we get for the first one? What is f at 0? It is 1. Okay, we're just looking for the value of the function. There's a hole up there, so there's where it is. Limit as x approaches 2 from the left. Okay, remember that's what that little negative sign means. What value are we approaching on our function 4? Okay, so it's getting close to the hole. And then the limit as x approaches 3. It is 0. Remember, if it doesn't have a sign, we got to think about both directions. Doesn't matter if it's not defined there. We're just talking about what are the y values doing. Okay. All right, so let's look at the next two. The next two involve a little bit of algebraic principle, all right, to get those. Because if I plug in -5, what's going to happen? It's going to equal 0, okay? Now, we could do this using L'Hopital, but let's do the algebra, okay? And then we'll talk about L'Hopital later on down in another unit. Were you doing L'Hopital? No? Okay, you're doing the algebra, which is cool, okay? With the algebra, we have to remember that we can factor, and we keep the limit notation, right, until we've completely reduced and simplified. The bottom would simplify to x plus 5, x minus 5, and so we'd lose those x plus 5. So the limit I'm going to do is the limit as x approaches -5 of 1 over x minus 5. Then we plug in the -5, and so I get 1 over -10. Okay, so just algebraic, simplify. If you get indeterminate, 0 over 0, right, then we do a little bit of algebra. Now, with number 5, what's complicating this one? Yeah, that square root's nasty, right? If I plug 3 in, 2 times 3 is 6, plus 3 is 9, square root of 9 is 3 minus 3 is 0. All right, so we're definitely getting a 0 on the top. 3 minus 3 is 0 as well. Do you remember how we fix it if there's a radical?
Multiply the top and bottom by the same radical.
Okay, we do have to multiply the top and the bottom. Okay, but what does it have to be? Can't just be, it has to equal 1, okay? And we want to multiply by the conjugate, all right, by the conjugate. So square root of 2x plus 3, instead of minus 3, we put plus 3, okay? Square root of 2x and then plus 3. So it's a conjugate, all right? The reason we use a conjugate is so that we're going to get like a difference of 2 squares, basically. We lose the middle term, all right, if we were foiling it out. So this would give me the limit as x approaches 3. Remember, we don't multiply out the bottom, okay? We leave it in hopes that we'll be able to reduce. Square root of 2x plus 3 and then plus 3. All right, the only part we multiply out is where the radicals are, okay? And so if I do that, bless you, okay? We'd lose the middle term, so square root of 2x plus 3 squared would be 2x plus 3, okay? Minus -3 times +3 would be 9, okay? All right, and then we're going to simplify a little bit, right? Right. So if we simplify, still got my limit there. Limit as x approaches 3. This would give me 2x minus 6 over x minus 3 square root 2x plus 3 plus 3. Okay? Now that doesn't look like I helped myself very much. Okay? Anything we could do to make it where it would help me? Yeah, factor out a 2 in the numerator. All right, so that gives me the limit as x approaches 3 of 2 times x minus 3. Then we've got an x minus 3 in that nasty square root. Okay, and we're going to lose that x minus 3. All right, because that's what was creating our 0 anyway. All right, and so then hey, okay, yeah, you're good. Okay. You're welcome. All right, so now we can actually substitute in our 3. So that's going to give me 2 over the square root of 9 plus 3, or 2 over 6, which is 1/3. Okay, so multiply by conjugate. Remember, you can do that if it's in the numerator or if it's in the denominator. It doesn't matter. Okay, we take the radical and then we switch the sign of whatever's being added at the end. Okay? It's just been a hot minute since we've done all that nasty algebra. Okay? Vaguely familiar in the cobwebs? Okay. Next thing let's talk about is horizontal asymptotes. Okay, and then even though it's not on here, we're going to talk about vertical asymptotes as well, how those two limits are different in terms of what we do. Okay, so when we're doing a horizontal asymptote, we have to think about the limit as x approaches positive and negative infinity. So we're basically going to do two limits, right? It's always the limit as x approaches positive and negative infinity of the end behavior model. Right? So horizontal asymptotes, limit as x approaches infinity of the end behavior model. So let's be careful right here. Okay. Let's pick out our end behavior model. Okay. Remember, end behavior is the highest degree term of the numerator and the highest degree term of the denominator. The one of the denominators is pretty easy. It's 3x. Okay. Highest degree term of my numerator is that 4x squared, but it is under a square root. Right? Now, when I simplify that, okay, 4x squared, we could have a positive or a negative value there, all right? Because if I square it, it's still going to be what? Positive. So we would say that it's the absolute value of 2x, and that's important, okay? Because that means I could take a positive value for 2x, or I could take a negative value for 2x, all right? So when we think about doing those two limits, if I take the limit as x approaches positive infinity, okay? The limit as x approaches positive infinity. This would be a positive 2x over a positive 3x. What would that reduce to? 2/3, okay? And the limit of a constant is that constant, so that's a horizontal asymptote, okay? So I'd have a horizontal asymptote at y equals 2/3, right? But I also have to consider the limit as x approaches negative infinity, okay? So if I'm doing negative with that absolute value, it would be negative 2x divided by 3x, which simplifies to what? Negative 2/3. And that limit is going to stay negative 2/3. So we have two asymptotes, 2/3 and negative 2/3 for our horizontal asymptote.
So would it not always stay the same?
What do you mean?
When you wrote that limit out, you said it equals negative 2/3, and you said it's going to stay negative 2/3.
Right, because it's a constant. So the only time that it wouldn't, let's say it reduced to 2 over x, right? Because if I take 2 over a really big number, it's going to approach 0. So you're either going to get two options. You're going to get a value that you can reach, a constant, or it's going to be 0, or we don't have an asymptote. Okay? Now, let's talk about vertical asymptotes and how they're different. We're going to use the same problem, right? When we do vertical asymptotes, we're talking about zeros of the denominator. Okay. And so we're going to be able to guess where that asymptote is because I can see the 0 of the denominator, all right? What we will have to prove is what the function does around that asymptote, okay? And so if I'm looking at this function we just had, 3x minus 5, what would be the value of my vertical asymptote? Yeah, where would 3x minus 5 equal 0? 5 over 3. Okay, so what we're going to have to look at is the limit as x approaches 5/3 from the left, and the limit as x approaches 5/3 from the right. Okay, so if you remember, this is where we chose values that were close to that asymptote, and we plugged them in. If I got a positive, it was positive. If I got a negative, it was negative. Okay, and it's always an infinity. And so what I would do is choose something close to 5/3. Well, 5/3 is pretty close to 2. All right. So if I'm coming from the left of 5/3, 2 would come from the left side. So let's plug 2 in. So if I plug 2 into the function, 2 squared would be 4. 4 times 4 is 16 plus 7. That'd be a positive on the top. And then 3 times 2 minus 5. 6 minus 5, that'd be 1. That'd be positive. So if I'm coming in from the left, all right, positive over positive. Is that right?
Wouldn't that be coming?
That's coming from the right, thank you. Yep, because it would be greater, right? So if this is 5/3, this would be 2. Yeah, so it would be the right. So I'd get a positive over a positive, so it would be positive infinity. Okay. All right, and then what could we choose coming from the left? 1. Yeah, we could choose 1. And so if I plug 1 in on the top, I'm going to get a positive, all right, because everything's added underneath there. On the bottom, 3 times 1 would be 4 minus 5. That gives me a positive divided by a negative, so negative infinity. So you're just checking values close to that asymptote. All right, so vertical asymptotes, it's the limit as x approaches. Oh, my Lord. You just never know what's going to happen in Nashville. A school employee was stabbed to death out in front of an elementary school in Nashville today.
By elementary. By an elementary.
Oh, I don't know who by, but still, yikes. Okay. Ugh. All right, horizontal asymptotes, vertical asymptotes. They're just things we have to review. We've not done them in a while, okay? All right, let's jump to continuity. Remember, continuity is a 3-part definition, okay? If a function's continuous at A, all right, 3 things. F of A exists. The limit as x approaches A of f of x exists. And those 2 things are equal. F of A equals the limit as x approaches A of f of x. Okay, so the limit has to exist from both sides. The function has to have a value, and the limit and that function value have to match. All right, that's the 3-part definition for continuity. And if you're asked to prove that continuity exists, that's what you got to do. All right, so if we can be continuous, we can be discontinuous. All right, so let's think about all the different types of discontinuities that we have. We have 3, removable, jump, and infinite. Okay. What's a removable discontinuity the same thing as? A hole. Okay, so if we draw an example, we're just going right along, life is good, just kidding. All right. Could we fill the hole, or could they put a dot there to replace the hole? Sure. Okay, but it's still a removable discontinuity. Okay. That is where f of A does not equal the limit as x approaches A. All right, so that's what's happening there. If we think about a jump discontinuity,
It approaches one value at one point and another.
yep, okay, the function approaches one value from the left and another value from the right. Okay, so the 2 limits are not equal. All right. And then an infinite discontinuity. That's a vertical asymptote. Good. Right? So my picture could look different on each side of the asymptote. Okay? Could approach the same direction or different directions, but they will go up or down. Okay? Okay. We want to make something continuous. Okay. We want to find the value of Q that will make it continuous. So let's think about what we would need to prove is true. Right? Because it's piecewise, what for sure has to be true about each piece? Yeah, the limits have to be equal, all right, from both sides, and they're pivoting around 1, okay? So we're going to take the limit as x approaches 1 from the left, and we're going to take the limit as x approaches 1 from the right. If those two limits are not equal, the rest of it doesn't matter, okay? So if we plug in from the left, we would use the top piece, so qx plus 3, which would give me just q plus 3 if we plug in 1, right? The second piece, we do x plus q squared minus 10, right? So if I plug that in, I have 1 plus q squared minus 10. And now we take those two expressions and set them equal. So q plus 3 would have to equal 1 plus q squared minus 10. They love this problem. You can count on seeing it. All right. Go ahead and solve. Okay, we're going to end up with a quadratic equation here. So let's make it all equal 0. So I get 0 equals q squared plus q, and I've got negative 9 minus 3, negative 12. And then we're going to factor. And so what values of q would work? Right, so solving a quadratic on that one. Okay, it's a little bit of algebra on that one. Main part is understanding if those limits are not equal, it cannot be continuous. Okay, so that's where that comes from. All right, number 8 walks us into one of our big 3 theorems. It says, given selected values of the continuous function h of x, so continuity here important, what's the fewest number of times h of x is 43 on the interval from 0 to 30? H of x meaning the y values, okay? How many possible times could we get 43? We don't have every value, but we know it's continuous, and if it's continuous, we don't skip any values in between, okay? All the y values and x values would be accounted for, all right? So where could we skip All right, would I probably hit 43 at some point?
0 to 5.
0 to 5, because I go from 100 to 440. All right, 10 to 15, because I go from 40 back to 110.
15 to 20.
15 to 20, I'm going from 110 to 30.
25 to 30.
25 to 30. So there's those y values are changing. So we have 4 times that it could happen. All right, this is the intermediate value theorem. Okay, IVT, intermediate. All right, the intermediate value theorem works when we have something that is continuous on a closed interval. Okay, it applies to both the function itself and its derivative if I know the derivative values. Okay, so it works on both, but we'd have to know those values, all right, to be able to find it. Okay, that is your intermediate value theorem. I can't go from 110 to 40 without passing through 43. Okay, so I can't go from a speed of 55 to 60 without passing through 57. All right, to get there. Always think speed, all right? We are addressing y values. Anytime it talks about a value theorem, it's talking about y values, okay? We use x to tell us where it happens, but it's talking about what happens to the y values, okay? A value theorem, okay? All right, then we get into properties of limits, all right? Same properties that we use with almost everything we did moving forward, derivatives, integrals, the whole 9 yards. So it gives me some limits, and it wants me to find the limit as x approaches 7 from the right of v of negative x minus 5c of x. And there's something a little weird in this one, okay, that you've not seen before. I'm going to just write down what they gave me. Limit as x approaches 7 from both sides of v is equal to 6. Limit as x approaches negative 7 of v is positive 3. And limit as x approaches 7 of c of x is 5. All right, so that's what I was given to start. And now here is the limit it wants me to find. Limit as x approaches 7 from the right, v of negative x minus 5c of x. Okay, now the only issue I see here is that this v of negative x, right? That's not defined. I have v of positive x. Okay, so do you see where that's an issue? All right, and so let's look at the second one. All right, the second one I can mess with. It's negative 5. We're going to keep. I have the limit as x approaches 7 of c of x. And because it's just 7, I know it's true from the right or the left. And so how much is that second limit equal to? Okay, it's equal to the 5, right? Now, what's different here about having that negative inside the angle? It's about that transformation. And one of the things the limit allows me to do is to switch it to the limit as x approaches negative 7 of v of x. It lets me switch those two. So if I have a negative inside, I can switch it to make it positive by making the boundary that I'm approaching negative. So I just switch where the negative is, all right, which is allowed, all right? So do I have a limit as x approaches negative 7 for v of x that I was given? Yeah, it's 3, all right? So 3 minus 25, which would be negative 22, all right? So that one's weird. I don't think we've seen one that's done that before, all right? But that is allowed. You are allowed to do that, to switch the two. Fake it. Fake it. God bless America. Okay. So just wanted to show you that because I didn't think we'd had one like that before. Okay. All right, let's look at this next one. So to find the limit as x approaches 0 of x squared sine of 1 over x. Okay, if I plug zero in there, I get sine of something undefined. Okay, and 0 squared. So we can't evaluate this limit like we evaluate everything else. All right. This is actually an example of what we call the squeeze theorem. Do you remember when we talked about that? It's been a hot minute. This is the squeeze theorem. We're squeezing this sine function between x squared. If you remember from pre-cal, we had x squared, and then we put that sine function in between it. Okay, so if I graphed it on my calculator, it would look something like that. Okay, so what has control over what sine is doing? The x squared. Okay, so we can switch this and take the limit as x approaches 0 of x squared, and the limit as x approaches 0 of negative x squared. This is about knowing that this is a damped trig function. And to do that, we use the squeeze theorem. Okay. Because the quadratic controls what sine's able to do. All right, it's going to push it in there and squeeze it between. And so what's the limit as x approaches 0 of x squared? It's 0. And what's the limit as x approaches 0 of negative x squared? 0. Okay, so this whole limit is equal to 0. All right, and that's the squeeze theorem. All right, bless you. As long as that sine function is squeezed between, all right, x squared and negative x squared, I can do the limits of just the two outer parts, and that will give me the limit of the inside part. Okay. Now, the yellow sheet that I gave you has what we call justifications on it. So if you're trying to prove something, it tells you what that statement should look like or what you should use to prove that it's true. And that's where we're headed with this last couple of questions. All right. And then I'm going to let you guys do a little bit of work. All right. So we're going to look at a couple of tables. All right. To talk about what's happening and to look at some application of some theorems. And it says tram A runs back and forth on a straight north-south path between an amusement park and an adjacent parking lot. Tram A's velocity, measured in meters per second, is given by the continuous function v sub alpha of t, where t is measured in seconds. Selected values of v sub a of t are given in the table above. All right. So if it's giving me velocity, is it giving me function values or derivative values? Derivative. Velocity is a derivative. Okay, and we hadn't really gotten that far in Unit 1, but that's what it's saying. Okay, do the data in the table support the conclusion that tram A's velocity is negative 10 meters per second at some time between 40 and 100? Okay, would we hit negative 10?
Yes. No, I lied.
I lied. Okay, because what interval is it asking me on? 40 to 100. Okay, and that's the biggest thing they'll do because you know IVT and you're excited that you know IVT and you're looking at that table and you're like, I got it! And they restrict the domain on you. Okay, so that's what they'll do to you. All right, so you really have to read the stem. Okay, the question stem. Thanks for doing that, Parker. We appreciate you. Yep. Okay. You're the model of what not to do today. Okay. Tomorrow it'll be somebody else. It's okay. We have to, right? If y'all didn't make any mistakes, we'd never learn anything. Okay. All right. So. All right. So this time we would say no. Okay. So it asks, does it support it? We would say no. And then we have to say why. Okay. When we give a reason. Okay. So we would say because v sub alpha of t is continuous and changes from 10 meters per second to 4 meters per second on the interval 40 to 100. Okay. By the intermediate value theorem, and you can actually write IVT. They know what that means. V sub alpha of t will not equal negative 10 meters per second on that interval. Okay, what they're looking for here is no and IVT. All right, and a statement of continuity. All right, because IVT only works if it's continuous.
So you don't have to say like, it's not definitive that it will, you could, you just say no.
Yeah, we just say no. Because based on the data that we have, we would say no. Yeah. All right. Let's look at another one where it's using IVT. All right, it's using IVT. So it says water's pumped into a tank at a rate modeled by, notice it's a calculator active question. All right, WT equals, and we've got all that. It's pumped into at a rate. Water is removed from the tank at a rate modeled by R of T liters per hour, where R is continuous and decreasing. Selected values of R of T are shown in the table. Okay, so is there a time between 0 and 8 when the rate at which water is pumped into the tank is the same as the rate at which water is removed from the tank? Explain why or why not. Okay, so we're looking for, is there a place where R of T would equal W of T, right? So I think the best thing to do at this point is we need to know what some of those W of T values are, okay? Can we get them at these values that they've given me? And how would we get them? Yeah, we just put it in the function itself, okay? You could put this in y equals. You can set up your table to ask mode for independent if you wanted to. But we need to get these values between 0 and 8 for W of T. Somebody have those values because I can't read what's on my paper.
2,000.
Okay,
1,902.5.
okay,
1,275.3.
okay,
300.6. 333.
okay,
And 81.524.
okay. So we're looking at the R and the W values, all right? Is there an interval where they would both be the same rate?
Yes.
Yes, which interval? 3 to 6. Okay, 3 to 6. They would be the same. Okay, now we could state that as, is there an interval? We would say yes. By the intermediate value theorem, the rates would be equal on the interval from 3 to 6. Okay, so you could say it like that, just that simple. All right. Another thing that we could have done is we're trying to see, is there a place where RFT minus, RFT minus WFT, right, is equal to 0, or WFT minus RFT is equal to 0. Right. One of the, I messed up here. We would say because RFT and WT are both continuous. So in order to use IVT, we have to state continuity. All right, even though it said in the beginning that it was, all right, we have to state it in order to use IVT to prove. Okay. Now, one of the things we could have checked was the beginning at time 0. All right, so that would give me 2,000 minus 1,340, which is greater than 0. And then we could have done W at 8 minus R at 8, which would be 81.524 minus 700, which is less than 0. And then because of IVT, all right, I started with a positive, ended with a negative. I'd have to pass through 0 at some point. So you could use that also, all right, as a proof. All right, in order for them to be equal, the difference would have to be 0. All right, so this is an alternate way to prove. So I just wanted to show you both of those. Okay, that's that whole rate in, rate out concept that we get to a little bit later on. All right, but that's how it works. All right, last one. They like to do lots of things with continuity and defining functions in lots of different ways, okay? So it says, let G and H be continuous functions, that's important, such that G of 5 equals H of 5 equals 1, okay? In other words, G at 5 is equal to 1 and H at 5 is equal to 1. Okay, so the functions defined, G and H, are defined at 1. Let K be a function satisfying this inequality. Right? And it's true as long as X is on the interval from 3 to 7. Okay? So, G, H, K is in the middle. Right? H is the largest, G is the smallest, K is in the middle. And it asks me, is K continuous at X equals 5? Okay, so that's what it's asking me. Right. So if G of 5 is 1 and H of 5 is 1, right? And we know those G values, okay? What has to be true about K at 5 for that inequality to be true? K of 5 is equal to 1. Okay? So now we know that the function is defined. K at 5 is equal to 1. That's a function value. All right? The next thing we have to prove are the limits. Okay? The next thing we have to prove are the limits. So we would look at the limit as x approaches 5 of g of x. Well, that's the same thing as g at 5, which is just what? 1. Then we'll look at the limit as x approaches 5 of h of x, which is just h at 5, which is equal to 1. Okay? Then we'll do one last limit, the limit as x approaches 5 of k of x. All right? That would be k at 5, which is just 1. Okay? So we had to prove that all those things were equal. Right? We had to prove that all those things were equal. Right? So we would say on the interval from 3 to 7, the limit as x approaches 5 of g of x is less than or equal to the limit as x approaches 5 of k of x is less than or equal to the limit as x approaches 5 of h of x. Okay, so that inequality holds true for the limits. All right, it was true for the function. It's true for the limits. All right. Therefore, okay, because we're speaking only of k. So therefore, we're going to take that limit as x approaches 5 of k. It's going to be between x and 1. All right. And, between 1 and 1. Which tells me that the limit as x approaches 5 of k of x is equal to 1, which equals k at 5. The function k is continuous. Add x equals 5. So we will get used to looking at these problems and writing the reasons, okay? We'll do lots of that. That's what we spend the bulk of this 4 weeks doing, is learning how to write those reasons so that we get all those points, okay? We'll practice a little bit of the mathematics, and then we'll go back and we'll talk about the reasons. The yellow piece of paper that I gave you is that justification guide. This is just really helpful, okay? And so if we want to justify that something is continuous, then we have to state or show the following. If we want to show that something is a relative maximum, then we have to state or show that f prime changes from positive to negative at that value. So like there are things, this is a great reference, all right, when you're trying to work through a free response and figure out how do I prove it's true, okay? Like I know it's true, but how do I prove it's true? And so use that, download it, keep it somewhere where you can see it, okay? It is attached in your Google Classroom. Now, I've given you 2 things for additional, helps if you turn your pen on, for additional practice, okay? I gave you a circuit, all right? It's a limit circuit, so it's self-checking, all right? But I also gave you a document that's called AP Review Limits and Continuity, all right? And it has just lots of good practice, okay? Not multiple choice, but it's just good practice. Do a little bit of that, okay? One of the things I need you to do for me every day is to do a little calculus every day, okay? I'm not asking you to do hours and hours of calculus every day, all right? ridiculous. Nobody's going to do that. But if you wait until 2 or 3 days before the exam and you try to cram, you will not be ready. Okay? I'm just telling you, you won't be. And I know you, Himmel. All right? So, not to call any names. All right? But, Samuel. All right, Justin. Solomon. Okay, right? Parker. Okay, you've got to do a little bit every day. Okay? A little bit. Not a lot, but a little bit. Here's why. All right? Every day when you come into class, you're going to have what's called 5 for 5. 5 multiple choice questions that cover the unit that we covered the day before. All right? It will be graded. You'll do it independently. You'll put your answers in on Google Classroom, so you'll get immediate feedback. You'll know how you did. Okay? And then you get to keep the 5 for 5 sheets so that you have it, all right, to help you review. All right? So it's 10 points every day when you come in. 5 questions, 5 for 5. All right? There will be calculators. Sometimes they're calculators, sometimes they're non-calculator. It'll be specific. You'll know. All right? Wrap-ups. Okay? Wrap-ups are going to have probably 3 questions a day. Right? So that's 3 points a day. All right? You're going to get credit whether it's right or wrong. All right? Because it's wrap-up. We've just talked back through it. So you will get your credit for whether it's right or wrong. Okay? So 3 questions every day. So this is taking me a little bit more time to throw together. Right? Because I'm throwing it on Google Classroom. All right? So what I'm going to do is I'm going to give you the wrap-up every day. All right? So that you have it. And then you'll be able, it will give you immediate feedback whether you got it right or wrong. Okay? It won't give you the correct answer, but because I love y'all, but you talk to each other. So, but it will tell you if it's right or wrong. Okay? And then we'll discuss before we leave what the correct answers were. All right? You didn't get them all right. So let me give you this. All right? This is your wrap-up. For today. Okay? I prefer you do it independent. Okay? I want to see if there's something else we need to talk about again. All right? And then we'll talk about it as a group. Okay? So all you'll do is put it in your answer.